I'm Alexey Kozhevin, data scientist from Gazpromneft, Russian gas and oil company, and our team develops solutions to optimize some processing in field exploration. Today, I will show you the typical stack of technologies that we use when work on the project to produce reproducible solutions. First of all, let's talk about machine learning in geology, or more precisely in gas and oil exploration. Large collectors with a simple structure like that have been discovered and developed, and now we have to work with smaller and hard discovered collectors like that, and simple models that were developed in the previous century is hardly applicable for such tasks. So machine learning has a good opportunity to produce really good solutions which can help experts to analyze a large amount of data which produces from seismic exploration. So our team produce open source solutions for gas and oil, and also we have Batchflow library. It's a Python framework to deal with common machine learning. For example, you can use if you have some computer vision task. It has very flexible tools to construct the whole process of data loading, data processing, model training, data parallelization, and you can organize all the process in simple pipelines. I will show you an example later. And also we have few libraries for special tasks in geology. For example, SeismicQB. I will show you it later. It's a library for seismic interpretation, and today we will solve one task from this field. So first of all, I'd like to talk a little bit about what kind of data we have. One of the first stages of field exploration is seismic analysis of the field. In some sense, we have 3D representation of this cube of yours, and it's enough today to understand what inputs in our models we have. For example, it's sliced from real seismic cube. You can see some structures. It's actually bounds between different layers of rock, and it's a very important task to construct automatical solution to find these bounds, because now there are a lot of routine in that process. Of course, there are some instruments to solve the task, but it's commercial instruments, and actually they are not too accurate. And also there is a special kind of surfaces in this 3D cube that we need to find. It's so-called seismic faults. You can see that we have some bound with some discontinuities in it, and the task is to segment this data to find these faults on the whole 3D cube. And today I will show you an example of project how we can do it on real seismic data. Today, first of all, we will talk about technology, not about the task. So I will show you the whole process from project template creation to final solution, almost final in some sense, that consists of the following steps. First of all, we create environment. Here we use Docker and Kubernetes. Then we create project template with some structure, which is common for all projects. It's very important. Then we import data from our storage using DVC. Then we create baseline solution. We use Batchflow and task specific library. In our case, it will be SeismicQB, and perform some research using multiple GPUs, because if you have cluster of GPU units, it's very important to utilize all of them. And for example, you can train a lot of models to find the best one of them. And finally, when you construct a final solution, you can wrap it in some graphical interface. So let's start with our practical part of workshop. So please check your emails, and if you have an email, you will find address like that with some port. When you will open this page, you will see starting interface of JupyterLab. So please type your password from emails and log in. I will wait a few minutes. If you have any problems, please type into chat and we will help you. While you are logging, just a few words about our libraries. We have two repositories at GitHub: Analysis Center with Batchflow library for common data science, and Gazpromneft GitHub, where you can find other GSNDL specific libraries. We also have Medium blog with papers about our solutions, some more detailed papers in Archive, and course in YouTube for geologists about our instruments. All our libraries you can find in the top of our repository. For example, here you can find SeismicQB with necessary description and documentation, and we will use it a little bit today. So first of all, let's start with our environment in JupyterLab. Wait a second, I'll check. Where is it? Okay, I hope everything is okay, because
yes, I
can find interface of Zoom. So
don't worry, it's okay.
Okay, so let's start with our environment. When we start our project, we use our Docker container where we have all necessary libraries for data science and other common Python libraries. You can check it, for example, in some notebook if you will create, but we will start with creation of project template. For our project, we use custom cookie cutter template. You can find it in our GitHub. So please use the following link. It's so I will try to find, yes, chat. Where is it? To send it into a chat. How I can do it?
It seems to do it, you need to stop sharing and then send it to chat. So if you don't do it now, really, probably we can do it later.
Okay, so just let's type this link in your terminals. It's just cookie cutter, https://github.com analysis center ML project template. So please retype it into your command line in JupyterLab. You can create terminal if you will press plus in interface. In that case, for example, you can create your project with some name, for example, demo. You can create a name for your repository if you will use it in GitHub. In our case, we can use defaults for creation. For example, here you can say what library you want to use as submodel in your project. For example, if we will work with some common ML task, we can use batch flow, so type 5. All other steps, just press enter for everything, because it's not too important now. I want just to show you an example of a repository, but here there are a lot of okay, batch flow is not a good idea for. We can recreate a demo. For example, let's choose Seismic QB to create DVC repository, because by default here we will create a DVC repo inside of the project, and let's use it with Seismic QB library. In that case, you will create a folder in the root, in that case, of your Docker container. Here you will see some structure for your project. For example, special folder for your data sets, special folder if you need some Docker containers, folder for your notebooks, and so on and so on. And also here we have Seismic QB library submodel, SRC folder for some utils, folder for test, and so on. And it's very useful because when you work in team and you have a lot of projects, sometimes it's difficult to switch between them if they have different structures, and it's much more easy if you see the similar structure and you know where you can find tests, when you can find SRC. And besides, it's just a good practice to have a good structure in your project, because when you will show it for your colleagues or for some, in our case, geologists, it's easier to demonstrate structure if you have it for all your projects. But in our case, we will use example of project for false detection. So we have also repository in our GitHub, and to clone it, just type git clone this link, https://gazpromneft false demo. And it's very important to add flag recursive, because in our library we have two submodels and recursive. We have two submodels, and it's very important to use it, because otherwise you will have empty folders and we will have some problems. Here you can see that we clone Seismic QB library and also clone batch flow, which is part of Seismic QB. As I said before, we have a library for common data science, and we use it as a core library for all our projects. So if we will return to our root library here, you will see false demo folder. This is the same structure. We can see the same structure as our demo project, but also you have a few notebooks that we will run in a few minutes. But also, when you work on project, you need some data. And of course, I think everyone knows how to use Git to control your code, but last few years shows that it's very important to use similar technologies to control your data set. And of course, one of the instrument that we can use is DVC. And in our case, we also have the third repository that we need today. It's GitHub Gazpromneft Seismic Data Demo. It's our Git repository chained with one real seismic cube. So actually, it's a repository just with some meta information about our data sets, not with real seismic data, because you can see that we clone it very fast. So let's go to that folder, cd seismic data demo. And here we can find just one DVC file. Please type DVC pool and the name of that file. In that case, we will pull all necessary information about Seismic Cube from our DVC repository. Actually, it's just a demo repo. In real life, we have remote on other servers, because we have a large amount of data, of seismic data, and we use a lot of virtual machines, and it's a very frequent task to clone it from our remote repository. But to make loading faster in our workshop, I just created copies of that demo repo in your machines. So you can see that you clone your data, and you can call ls command, and you can see that you also have, you can check it also in browser. Okay. The command is DVC pool and the name of your file in seismic data demo folder. Which is called seismic data demo. So let's repeat it another one time. If you are in notebooks folder, you have 3 folders now. One of them is seismic data demo. Just go to it using cd command, seismic data demo. And then call the command DVC pool and the name of this cube. It's the only one file which will be in the folder after cloning of the repo. And I can also call it another one time, but actually I already have the cube in that folder. So you can check that finally in the seismic data demo folder, you will have this folder and you will have some data. It's our raw data, some annotation, and I will talk about it now. So let's start with the project. When you create your project template, you start working with your data. And for example, let's run the second tutorial, show data, in the false demo notebooks folder. And here you can see demonstration notebook to show you how we can work with seismic data using SeismicQB library. Just a few words. Here we need to add a path to import classes from the library. A few words about format to store seismic data. It's a SIGWAI format, and it was designed just for storage many years ago. And it's actually binary format for collection of seismic traces. Seismic trace, it's one line from the top of the cube to the bottom, and it is called trace. And each trace stores separately in that format, and it's really slow. So let's load that cube using just a second. What the problem? False demo. I haven't submodel seismic QB. Wait a second, please. What's the problem? So, yes, I make an error. So I will try to clone it another one time. The problems of live coding, actually. So seismic QB, yes. We have everything here. So let's start. Show data. And another one time. If you have similar problems, please type into chat. Yes, everything is okay now. So here we import a seismic geometry class, which is a special class for data loading. Here we define the path to our cube, which is import from DVC. And you can use methods from this class to show some slices. Here you can see one slice of seismic data. Here you can see our horizons. You can see fault. You can see that we have some discontinuity from top to the bottom of this cube. And as I said, the problem with SIGWAI that it was not designed to fast data loading. It was designed for data storage. So if we time loading of one slide, we can see that it's too because when we will train our models, we have to load crops from our data, and we will load a lot of crops, and it will be really long if we load one slide in that time. Of course, we can solve some problems by caching. If we will load the same slide of seismic from SIGWAI, we will see that because it's cached, it's much more faster. But to make loading of initial loading of slides faster, we create special storage format for our cubes. We use HDF5 format, and we convert each SIGWAI cube into it. And in that case, we have prepared converted cubes in our data set. And you can check and compare times of loading from SIG-Y and from HDF5. Of course, there is one problem with that format. It's much heavier than SIG-Y, but if you have large storage, it's not a big deal. And finally, let's check not only our inputs for models when we will train it, but also annotation. For it, we use two additional classes from SeismicQB, Seismic CubeSet and Fold class. And firstly, we create dataset where we add our cube and also append our annotation from the folder, which is stored in the same library, in the same folder as cube. You can see folder inputs, folds, and in that folder, you have annotation for each fold in that cube. Actually, each file include coordinates of each fold in data, and we will use it to construct masks for our neural networks. No, and also we have check some crop from data. About SeismicQB, you can read in documentation in our repo, but let's start to work with models. If you will go to notebooks and you will open the third notebook, baseline model, you will see a real model, which is trained on seismic data. And let's go through cells of the notebook. As I said before, the task is fault detection, and we solve it as semantic segmentation task. We will use a unit-like model to construct mask for each crop of data with zeros in pixels without faults and ones in the places with faults. Here we have necessary imports, of course. So very strange problem with JupyterLab. Let's restart it. Yes, very strange. I just restart kernel and everything is okay. So then everyone has a virtual machine with just one GPU, so it's not very necessary to define the visible devices. And then we start to construct our solution. The philosophy that we use when we working with projects is that we construct special libraries for each kind of data that we have. For example, when we work with seismic cubes, we define primitives to load data, to augmentate crops when you will train models, and so on and so on. And all common functional, which is common for different tasks, but dealing with the same data, we encapsulate in libraries. So when we work with fault detection task, we extend functionality of the library. We add special classes, for example, to represent each fault in data. And then when we add this functional into our libraries, which are open source, we then use them to construct real solutions. So in that notebook, we haven't any utilities, you almost haven't. We haven't long definitions of classes, functions, and so on. All of them are in library. And here we have just description of what we do to construct a solution of the task. So here we define path to our cubes. We create data set. It's a primitive to encapsulate our seismic data and annotation. We also define how we will sample data when we will train models. As you can see, we just call some method of dataset, but actually under the hood, we have really flexible instruments to define how we will create crops from our cube. So everything we can check in our library, and here we just construct a pipeline to train the model. We also can construct some plots in our notebook to demonstrate data, to plot some statistics for your cubes and so on. So the role of the notebook in the project to demonstrate the solution. When we create baseline model, we just create the first model to be sure that everything is okay, that data is good, and we can really train on a model. We haven't any problems in our library, and so on. So when we create our data set, then we define our model. Here, as I said before, we use BatchFlow as submodel of our project and of SeismicQB. And BatchFlow is a library which has instruments to define models in the following way. Here, we define a unit-like model where we define encoder, when we define decoder, where we define embedding. Here we use some extension of UNet. Here we also use REST blocks inside of UNet, and the plus of such usage of configs that we needn't to rewrite some torch model to use the whole sequential model or something like that and change something inside of it in some method. We just can create a highly parameterized model, which we can then change with such kind of config. Also, you define some parameters like loss function, what kind of optimizer you want to use, what decay, and other stuff. Then when you define your model, you define your pipelines. Here you define 3 parts of batch processing. First of all, it's loading. Here you also define some variables that will be used in your pipelines, for example, to store loss history. You add your model, which were defined by model config. Then you said how you will create positions for your crops. It's make locations action. Then you say that, okay, now I will load seismic data. Then you create masks for each. You normalize your data, and actually it's just a scheme of the processing. When you create your pipeline, you don't execute any methods. You just create plan of the processing, and also you create for here number of iterations that you will use, the size of prefetch that will be used in the training stage. But it's just plan of your experiment. And when you define each of them, loading pipeline, augmentation pipeline with some augmentation methods for crops, and when you define your training step for the model, where you define inputs, targets, and what you want to store when you train your model. In our case, it's only loss history and predictions to plot them. When you define your pipelines, then you can sum them into one pipeline and also add dataset. Here we just use load template and augmentation template to sum two pipelines and to plot few examples of crops that will be used to train the model. Here you can see one crop. It's of size 128 and 512. You can see the mask of that crop. And on that stage, when we have images in masks, we can solve it just as semantic segmentation tasks. Also, you can check a few other examples. And then you create the whole pipeline, which consists of loading, augmentation, model training, and you also add data set. This shift means that we add data set to your pipeline. We also have special class notifier, which helps us to plot some examples of our data, of our images when we will train our model. Now we will not train a real model, which we will train too long. So we will train it just, let's check, just 10 iterations. And when we start our training, you can see loss function, examples of our images, masks, and predictions. And then you can check some examples on inference. Of course, because we train our models just for 10 iterations, we will have bad predictions, but it's just examples that shows that we have the similar pipeline to describe the inference stage of our model life cycle. And we haven't any long definitions here, but if you need to check some of implementations, you can go to library. So it's very comfy, and I think that it's good practice to provide good structure of your projects. So when you construct your baseline, then let's talk about what minuses of such approach. Of course, as I said, we have a lot of things under the hood in the library, but actually we train our model in the UPython notebook, and maybe it's not very good because sometimes it's hard to control some changes in notebooks, and also you need to define some data set steps creation. So for our models, please now I ask you to restart a notebook because we will need our GPU on the next notebook. So please call restart kernel for our baseline model. And then let's go to controller model. In our projects and in SeismicQB, we create special classes for each task. In my case, it's fault controller, which also encapsulate all this stuff described in the previous notebook, just in few methods. So we create special class fault controller, which has config. We described paths to our data. We described crop sizes and all necessary parameters that we need on the training stage. And then we just call, very strange thing. When I start notebook and the first time, it has some errors. So then when you create your baseline, you can wrap it into some controller. It's very important because when you will start experiments with your model, it's much more easier to store all parameters in one variable. In our case, it's config. And then all the following process is described just with that config, which can be stored in some YAML file, for example, something like that. But when you will change something, you can check it just in one file, but not in the notebook in some place where you define some constants, you define config and other parameters. You will have just one class with few methods. And I think it's very nice to have all things in one place. And also in our controllers, we add some useful stuff like monitors for GPU usage, memory usage, and so on. And also you can plot plot predictions for cube just with one methods without any problems. And also it's very important on the next stage. Please restart kernel for that notebook too. And let's go to the 5th notebook, controller research. And I think that I have to restart it, and then after execution of the first cell. So here you define the same config, you define the same controller, but what if you want to train a model with different parameters? What if you want to check different losses for your model? For example, when you try to solve semantic segmentation task with two classes, you can try binary cross entropy or binary dice. And also you can vary some parameter. In our case, it's what kind of transformations in the first layer of our neural network we have. For example, for seismic task, we can add instantaneous phase computation or not. And it's just a parameter of our config that we can vary in the following manner. Batchflow has submodel research, which allows to parallelize experiments with your models. And also, it's very important, it allows to parallelize models execution using multiple GPUs. So in our tutorials, we have just one GPU, but when we have multiple GPUs, for example, 8, you can train 8 models in parallel, and you don't need to use multi-processing. You just can use primitives from Batchflow research, which can train models in parallel and then store results of experiments in some special format. So also it has a way to define your grid for grid search. In our case, we have 2 parameters for 4 values, 2 values for one parameter and 2 values for the loss. In that case, we define domain, and then we create some meta pipeline. It looks like a Batchflow pipeline where we use research class. We define domain, which is just 2 parameters. We create instance of our controller with some name, with config, which is defined here. And we also define some parameters for results storing, because fault controller has save dir parameter. And when we will run our experiments, for each experiment research, we will create special folder. And to define the way to this folder, we use savedir and this expression. Then we say that we want to make dataset, train, dump model, and plot inference to check results on some slide of Seismic. And we don't need to create some special classes. We don't need to create a multiprocessing pool. We just use research. And if we will have a few GPUs, you can define, for example, 4 workers and say define devices parameter and define indices of GPUs that you want to use. And then you will train your models in parallel. When you will run Seismic Research, you will create a folder, Seismic Research, which have some special format of result storing. For example, each experiment will have some ID. Here we will store results of each experiment. Also, we have, of course, for each experiment config of this current experiment. We have description of the whole pipeline of the research. Also, we store some information about current state of the repository of the project. We save current version of commit. We store diff because, of course, when you perform experiments with your models, you don't commit every time your notebook. When you change some parameter, you can just change one of it, check research, but it's also important to store diff between current state of your repository and the last which was committed. And in that way, you can perform parallel experiments with your model. For example, we can see that outputs of the first model we can see here. We can check results in our folder. Here we have some additional information. We store our prediction, and it's very flexible stuff. I show you an example of usage research with fault controller, but you also can use it with your task. You just need to, for example, I have notebook research. Let's just open it. Here we can see an example of using research with Pascal segmentation dataset. Here we create pipelines to train the model, to test it, and we also create some domain of parameters that we want to try. We add our pipelines in our research and say that we want to save metrics, and then you just can execute all cells of this notebook. And as a result, you also will have some folder which will store results of your experiment with whole meta information. And you can use the research for your task, which is not connected with seismic interpretation and so on. So when you perform experiments with your models, you can check results, you can check metrics values, you can check the best model, and then as a following stage of that process, you just can wrap your model into a graphical interface. For example, for fault detection, now we haven't any graphical interface, but for other tasks, we already realized it, and now geophysicists in our company can use all these models and all these process defined by controller using on their work stations. So in few words, let's check the whole process of working on our projects. As I said, firstly, we create an environment. in that case, it's very important, because when we will try to reproduce our models, reproduce our results on other machine, we have the same environment, then we can import, we can clone our data sets and our code from GitHub and DVC repositories, and it will be the same for each case of cloning. Then we can perform experiments using special libraries for each task, and using research, which allows you to provide reproducible experiments. Reproducible in that sense that you can restart it, and if you will fix your random seeds and all the things, you will have really the same results. And then when you will have results or the model quality estimation, then you can check the best model and wrap it into graphical interface. And this pipeline is common for all our tasks, and we have to check different technologies and different ways how we can implement the whole stack. And by our opinion, it's the most appropriate way for us to make reproducible projects. So I think that's all. If you have any questions, please ask me.